welcome to the 6-6 notes, our last section of the chapter in dealing with similarity and proportions. So this one is just a little, we're not actually doing all the theorems in this section, we're just doing one theorem, and that is called the side splitter theorem. It's actually pretty easy to use once you get the hang of it. It'll make things go a little bit faster. You don't really need to use it in a lot of situations, but it makes things quicker and easier, and I'd like to show you why. Some situations, however, it is actually a little bit harder to use, and that might be confusing to you. I'll try to show you illustrations of both where it'd be easier and harder to use the side splitter theorem, but it's just a handy thing to know, and we're also going to prove why it works. Okay, so the side splitter theorem 6-6, the only part we're covering from 6-6. So, first off, let's say I want to solve for this length here, RQ. Let's call this X. I could actually use two methods, okay? So first off, notice that this triangle RQS is similar to this triangle RUT, okay? So RQS, this red triangle here, is actually similar to this black triangle here. Why? See if you can figure out why, given that these are parallel. Remember, parallel lines, oftentimes it's helpful to extend it out a little bit. Extend out this as a transversal. If you've got parallel lines cut by a transversal, think about what you have. Why could I call this little red triangle, this black triangle, similar? Well, if you remember from chapter 3, if I've got this angle here, and this angle here are congruent, right? These are corresponding angles. Alternate, corresponding, congruent, right? This is also corresponding angles here. Or you could have added angle R, which is congruent to angle R from the big triangle by reflexive. But either way, you could say that this triangle and this triangle are congruent, sorry, not congruent, similar by AA, right? Angle, angle, or R, angle R if you use that. So we could set up and solve, right, because they are similar. Let's think about that. Because they are similar, that means I know that the sides are what? If they're similar, that means by definition the sides are proportional. Right? The sides are proportional. So before I proved that these were similar triangles, I couldn't say anything, but now I know that these are proportional. So I could now set up and solve using the corresponding sides of the little red triangle and the big black triangle. Or I could go reverse, I could go big black triangle to little red triangle. It doesn't really matter. But let's go ahead and take a look here. So let me do that. So X is the little red one. I'm actually going to make a mistake as I set up this proportion. See if you can spot it. So little red triangle side is X. The big black triangle side is 9. So X to 9 is the same ratio as 4 is to, the whole thing is 10. Do you see my error here? X is the little red one, but this is not 9. This is X plus 9. So X is to X plus 9. X is to X plus 9 as 4 is to 4 plus 6, or 4 is to 10. This is a perfectly valid way to set it up. And if I cross multiply and solve, so I'm going to get 10x equals, don't forget your parentheses here, 4 times the quantity x plus 9, right? 10x equals 4 times the quantity x plus 9. Don't forget the parentheses, because otherwise you're going to forget to distribute. 4x plus 36. Okay. I'm going to subtract 4x from both sides. So I'm going to get 6x equals 36. 6x equals 36. If I divide by 6 on both sides, I get x equals 6. But often, not always, things are easier using the side splitter theorem. And I've mentioned the side splitter theorem, but I haven't told you what it is. It's going to let you set up the proportion as such. So instead of saying this guy to this guy equals this guy to this guy, which is true, we can simply look at this one right here and kind of just imagine this. We already kind of drew it as like a little split, like a fraction. I can say x is to 9. So this piece is to this piece. I'm just kind of splitting the side here. Equals this piece over this piece. So x to 9 is the same ratio as 4 to 6. Now that might seem kind of obvious, but it's actually not, because you look at this 9. This 9 is actually not part of any triangle. It's not an obvious thing that this should be a correct proportion. X to 9 equals 4 to 6. So it might help to draw a little line here, so you're just kind of splitting the side of the triangle. If we cross multiply, we get 6x equals 36, and x equals 6. And so you can see that it's oftentimes a lot faster to use the side splitter rather than the normal kind of little triangle to big triangle proportion. So let's go ahead and write down the side splitter theorem in our theorems sheet. Let's go to our theorems and postulates sheet on the back. So theorem 6.4, triangle proportionality, the side splitter theorem. Here's one thing I haven't mentioned, is that this requires parallel sides. So you need to have parallel sides here. If it is true, then it's going to divide the two sides proportionally. So in other words, if I have parallel sides, then I could say RT. So again, it's almost like you can draw a little dashed line here. This is like your fraction bar. RT to TQ, so this to this, is the same as RU, this is to US. It's like you're splitting the sides. This to this equals this to this. Now the converse is also true. So in other words, if RT to TU is the same ratio as RU to US, then I know that TU is parallel to QS. Okay, so if they're parallel, then the side splitter holds. If the side splitter holds, then they're parallel. And that's all we really need here. Let's jump back to side splitter here. And again, this one worked because we had parallel sides. Let's talk about why do we need parallel sides. So before we really get into using the side splitter theorem, let's prove why it works. Okay? So if I have parallel lines, let's talk about that. If I've got parallel lines, that allows me to say that angle 1 is congruent to angle 3. Think about that. Why could I say angle 1 is congruent to angle 3? Because of these parallel lines. Well, if lines are parallel, think back to chapter 3, we've got alternate, corresponding, congruent, same side, supplementary, and of course these are corresponding angles. So we can just say corresponding angles are congruent. Right? Additionally, 2 and 4 are also corresponding, so I can put arc, 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 arc. Okay, so because of that, I can say that this triangle here, QXY, this big triangle here, is similar to this small triangle QRS. Think about it. It's not because I have all the sides and all the angles, all the sides proportional, all the angles congruent. I don't have the sides, but I've got that shortcut method, right? Either AA, SAS, or SSS. And since I've got these angles here, that's because of the AA similarity postulate. Okay, so once I've got that, I could say QX to RQ is the same ratio as YQ is to SQ. Think about that. Why can I do that now? After these 3 steps, why can I say step 4? Why can I say that this to this is equal to this to this? Well, look at step 3. What did we just prove here? We just proved that this little triangle here was similar to this big triangle here. And if triangles are similar, what does that mean? It means all their angles are congruent. Yeah, we know that. But it also means that all their sides must be proportional, right? So we could say something like, since, this is not the technical way to write it, but since we proved triangle QXY is similar to triangle QRS, since we proved that they are similar, we know the sides are proportional. I'm sure there's a faster way to say that, but oh well. Since we proved that this triangle is similar to this triangle, we know that this to this equals this to this. We know the sides are proportional. All right, step 5. This one's a little bit trickier. Let's see if you can spot it here. Not 5. 6 is a little bit trickier. 5 is not that bad. QX, I can say is equal to XR plus RQ. Right? Let me do that again. QX is equal to XR plus RQ. Likewise, YQ is equal to YS plus SQ. this is actually something from the very first chapter, if you remember. I could say that this qx, this whole thing, is equal to this little piece plus this little piece. Or I could say this yq is equal to this little piece plus this little piece. That's just called the angle addition postulate. Angle addition postulate. Okay, in other words, I could say this little piece plus this little piece equals the whole big piece. All right, from 5 to 6 is a little bit confusing, so let me try to highlight a few things here. Look at step 4. I said the sides were proportional, so I said xq to rq equals yq to sq. Now look from 4 to 6. The denominators look the same, right? This is rq, this is sq, this q. What changed was the numerator. Look, xq became xr plus rq, and yq became ys plus sq. If you want to pause, think about why can I say that? Well, if you look carefully, look at xq, look at the missing link, step 5. We just proved in step 5 by angle addition postulate, which is kind of breaking it down, that xq equals xr plus rq. And that's exactly what we plugged in here. All we're saying is that instead of writing xq, because xq equals rx plus rq, xr plus rq, I can just plug it in, right? They're just twins. So this is simply substitution. Right? yq is equal to ys plus sq, right? yq is equal to ys plus sq. They're twins. So wherever I see yq, like right here, instead of writing yq, I'm going to plug in this guy. I'm just substituting it. And finally, where does that leave us? Look at, I have rq over rq. What is anything over itself? It's just the number 1, right? What's sq over sq? It's just the number 1. So I'm just going to subtract 1 from both sides. I'm going to subtract 1 from both sides. I'm going to subtract this sq over sq. Another way to, if I broke it down like a fraction here, you don't have to write this, but I could break it out into 2 different things, right? So this is a 1. If I subtract this, it goes away. I'm left with ys over sq. I subtract 1 from this side, I get rid of this. I'm left with xr over rq. And what is this? Look at the drawing again. xr over rq, so this to this equals ys to sq. In other words, this is the side splitter theorem. Okay, so we have just proven if I've got 2 parallel sides, I don't have to go and use this little triangle, big triangle thing. I can simply treat this like a split. I can just say this to this, right? This to this equals this to this. All right, so side splitter theorem works. I do want to emphasize though, sometimes it's easier, sometimes it's harder. Let's try some examples so you can see both types. All right, so first off, let's check. Method, we're going to do this in 2 different methods. I'm going to solve for this question mark. First, are these triangles, this triangle here and this big triangle here, similar? Well, because I've got this parallel lines, remember, I could add corresponding angles congruent here and here. Excuse me. So the answer is yes. These are similar. Excuse me. By AA. So first off, I'm going to sketch this triangle, a little red triangle, and I'll do big blue triangle. So first off, let's ignore side splitter. Let's just pretend like we know that little red and big blue are similar. Let's go ahead and set up a proportion. So question mark on the red corresponds to what is this length on big blue? Careful, it's not 6, right? Question mark to question mark plus 6, excuse me, is the same ratio as 2 is to, now it's not 3, right? The big blue, the whole side is 5. All right, so now we've got our proportions set up. We can go ahead and just cross multiply. So we're going to get 5 times this question mark equals 2 times the quantity question mark plus 6. We want to put the parentheses so that we can not forget to distribute here. So 5 times question mark equals 2 times question mark plus 2 times 6, or 12. I guess X would probably work better than question mark, but whatever. We're going to subtract 2 question marks from both sides. So we're going to get 3 question mark equals 12, divide both sides by 3, and I get question mark equals 4. So this method is perfectly valid, but I think this type of problem is actually a great example of something that works a little bit easier with the side splitter. So remember, as long as you've got 2 parallel lines here, you can almost just draw a line here and kind of treat this like the fraction bar. I could say this segment here, question mark over 6, is the same ratio as 2 is over 3. So this to this equals this to this. Right, that's the side splitter method, right? Question mark over 6 equals 2 over 3. I cross multiply. It's just a much simpler problem. I get 3 question mark equals 12 and question mark equals 4. Okay, so side splitter will often make things easier for us. Let's go ahead and turn over to the next page. And number 2, I would like you to do this on your own. You can either do either method. Method 1, treat it like 2 similar triangles. Method 2, use the side splitter, please. And we'll take a look after you try it. So go ahead and pause. All right, so method 1, I've got the red triangle here. Again, these are parallel. If you didn't see this and you didn't write that it was parallel, remember, you can't use either of these unless these are parallel. If they weren't parallel, you wouldn't be able to call the small red and the big blue triangles similar. So they are parallel though, so we can say that. Let's go ahead and take a look first. So if I use method, we'll call it method 1 here. If I use method 1, I would say x is to this whole side, x is to x plus 50, as 72 is to 72 plus 40, which is 112. So I'm just trying to cover this up. What's this? All right. So from there, I could simplify this by dividing both sides by 4, I think. Let's see, 8 will also work, but I didn't. I just used a calculator. So if I cross multiply, I get 112x equals 72 times the quantity x plus 50. I distribute, so I get 72x plus 3,600. I subtract 72x from both sides, and I get 40x equals 3,600. Divide both sides by 40, and I get x equals 90. So I could use the original method of proportional sides of similar triangles. That works. Again, this is, I think, though, is a main candidate for side splitter theorem, which is much easier with side splitter. So if we do the side splitter, we just get this over this, x over 50 equals 72 over 40. I simplified this by dividing by an equivalent form of 1. 8 over 8 is 1, so I just get x over 50 equals, this is 9, and 40 divided by 8 is 5. So cross multiply, I get 5x equals 450. Divide both sides by 5, and I get x equals 90. Just a lot cleaner and simpler. All right, so try number 3 and 4 now on your own, and then we'll pause and come back. So go ahead and pause, try number 3 and 4 on your own. Use any method. You could either use the side splitter method, or you could use, this little, proportional sides of similar triangles, whatever's easier. All right, so for number 3, hopefully you tried it now. I'm going to try the side splitter method first. Side splitter, okay? So if I do the side splitter, what I notice is this problem actually turned out to be harder with the side splitter method, side splitter theorem. Because why? Look, I've got x. If I try to draw this here and kind of split the side here, I get x over, well, what's this? What's this here? It's not labeled. 15 is this whole thing here. So I really have, if the whole thing is 15 and this is x, this little piece here is, where is it here? 15 minus x, right? The whole thing is 15. This is x. This is 15 minus x. And same thing over here. If the whole thing is 12 and this is 4, this part just here is 12 minus 4. This is 8. So I actually had to do extra work with the side splitter theorem, right? So I could do side splitter theorem is x over 15 minus x is the same ratio as 4 is to 8. Now, of course, I could simplify this to 1/2, cross multiply. It's actually not that hard, but in this case, it's actually easier to use the original method of method 1, I'll call it, using just similar triangles. Why? Because I don't need to know this is 8. I don't need to know this is 15 minus x. Because I'm given the whole side length, I could just say, okay, what is this? This is x. What is x's corresponding side length for the big blue? It's 15. This is 4. What is that's 4 for the little red triangle. What is the corresponding side for the big blue triangle? That's 12. So I can just say x over 15 equals 4 over 12, right? X to 15 equals 4 to 12. It's actually easier. Cross multiply. I could simplify this to be 1/3. So let's do that actually. Divide by 4 over 4. So I'm going to get x over 15 equals 1/3. And so I just get 3x equals 15 and x equals 5. Okay, so it's actually much cleaner and simpler in this case to use the original method of similar triangles. Why? Because we actually had the whole side already. So I guess you could say that if you were given the whole side, it might actually be easier just to use similar triangles. And if you're not, if it looks like this, it's probably easier to use the side splitter. So number 4, hopefully you've already done it. Let's take a look. You could do either method. If I do the side splitter, but first let me draw the triangle. I've got parallel sides. If I did the side splitter, let's see, I would need to know what this is right here, right? So this is 24. The whole thing is 24. This is 9. So this would have to be 15, right? 24 minus 9. 24 minus 9 is 15. Okay, and these are already filled in, so I'm good. So I could just use the side splitter and say 15 over 9. This to this is the same ratio as 35 is to 13 plus x. Okay. So that's the side splitter. If I did method 1, I would get, all right, so method 1, I'll just say similar triangles method. Similar triangles, I'm running out of space, I'll use a smaller pen. So 15 on the red corresponds to, what is bit blue? Well, this is given to me, that's quite nice, that's 24. So this problem, 15, 24, that's pretty easy, but now this side's a little bit more problematic. So the red side is 35. The blue side you have to calculate yourself, so that's a little bit more work. So this whole blue thing right here would be 35 plus 13 plus x, right? You're combining 35 plus 13 plus x, and you can combine these like terms. 35 plus 13 is 45. That would be 48 plus x. So again, we can use either method. In this case, it looks like side splitter's easier. So, you know, you might find yourself having to do a little bit more work. End result is that we've seen, though, it doesn't really matter. You can get the answer either way. I'm going to do side splitter here because it looks a little bit easier. But you feel free to use the similar triangles method. So we get 35 times 9. 35 times 10 is 350. So 35 times 9 is 350 minus one of those 35. So that'd be 320, what, 315? 315. And then 15 times 13 plus x. Okay, make sure it's the whole quantity 13 plus x. All right, so I get 315 equals 15 times 13. I'm not quite sure what 15 times 13 is, but I know that 15 times 10 is 150. I know 15 times 3 is 45, so 150 plus 40 plus 5, it's 195, plus 15x. Finally subtracting out 195 from both sides. So I get, let's see, I can do this in my head, because if I subtracted 200, that would be 115. Add 15 back, I get 120. All right. So now I divide by 15, and I'm going to get some kind of fraction here. So 120 over 15. So x equals 120 over 15. If I do this as a mixed number, 15 goes in 120. Let's see. I'm sorry, this is not a fraction. Let's see. 15. Let's see. 15 times. Let's see. When we guess and check here. 15 times 8. Let's see. 15 times 8. Does that work? Let's see. 10 times 8 is 80. 5 times 8 is 40. So yes, it looks like 120 divided by 15 is 8. Yep. So that's not a fraction. X equals 8. Okay, if we did this way, I'll just do it on the calculator so we can see it really fast. 24 times 35 is 840 equals 15 times, I'm out of space again, 48 plus x. 15 times 48 plus x. So we're getting large numbers here. So 840 equals 15 times 48. 15 times 48, which is 720, plus 15x. Subtract 720 from both sides. So 840 minus 720 is 120. And we're left with 120 equals 15x. And x equals 8, just like before. Okay, so our last question is, we have a shoe rack. And on the shoe rack, AB is 33 centimeters. 33 right here. BC is 27 centimeters. 27 centimeters. CD is 44 centimeters. And finally, DE is 25 centimeters. Why can I say for sure that this shelf is not parallel to the floor? In other words, this gray shelf here, it's marked by this BD line here. Why do I know that BD is not parallel to AE? Why do I know that this is not parallel to this based on this information here? Think about it. Okay, so if you remember back, we haven't done this one yet, but the original side splitter says if the lines are parallel, we can split the sides. The converse says if we can split the sides proportionally, this to this equals this to this, then I know the lines are parallel. So if I look here clearly, I could try to make a proportion. Look, 27 to 33, this to this, is that going to be the same as 44 is to 25? Clearly we can see that the denominator is bigger on this side, the numerator is bigger on this side. These are clearly not the same fraction. So since we know that this is not forming proportional, like side-splitted sides, we could say that BD is not parallel. Right? So we could say since segments are not proportional, right? We could say by the converse of the side splitter theorem, we could say BD is not parallel to AE. I'm going to do not in the black one. Not. BD is not parallel. All right, today we did the side splitter theorem. Also be flexible and be able to use the original method as well. Do whatever works best for you. Good luck.